All right, let's start. Hello, everyone. This is Dr. Yuzo. This is a ECE 318 Electronic Circuit 1. And today is our 16th lecture. Okay. And by the way, the lecture number is different from the number of the PPT slides. Please be aware of that. Okay. First of all, can you guys hear me?
Yep.
All right. Thank you. Thank you, folks. And also here I'm presenting the Gantt chart, reminding all of us that not many weeks left. It's actually more than half the semester is done if we exclude the final week. And here is also telling you how many assignments we need to do still, including homeworks, including the project, and including 2 more exams, right? So the next couple of months going to be very busy, obviously, and not only because of this particular course, but also other courses you have. So very busy. I think the only thing, only good news about this course is we don't need any so-called transition from the face-to-face to the post-Thanksgiving study, right? So everything will remain same. Okay? Even regarding the lab, yes, at that time, everybody gonna have at least 1 simulation lab experience. So I don't think the very last 2 labs gonna be a problem to you. Okay. So, any questions? Is there any feedback, any concern, any questions regarding this course? Anything you want to know more? Any questions?
When will we start discussing the project?
Here is look at the cell, which is obviously the end of next module 5. And so in terms of the specific date, will be obviously November 19th is the assigning day for the project. It is due by the final week. And we won't have any exam during the final week. So I kind of separate the due date for the project and the very last exam. And I believe this is going to be helpful. At least in the past, the students like this way. Any other questions we can discuss? All right, if no more, let's get the new module number 4 started. Okay, module 4 is should be something you're expecting. Okay, it's a AC small signal analysis for the Mosfet. Okay, chapter 4 in the textbook. You're gonna have 4 lectures to cover this entire content. And before going into the PPT slides, here is once again the table and course pattern. I always emphasize this. So you should be very clear what we are learning and where we at. Okay. So far we have done everything for diode. And now we have done the module 3, which is about the basics and DC analysis for Mosfet. Now we are here. Yeah, now we are here at this particular cell. Module 4, chapter 4, this AC small signal analysis. AC small signal analysis. And if you see how it works and how to analyze the circuit. Okay. The same pattern is expected for the next different transistor BJT. Okay. For module 5 and 6. Okay. All right. Now let's get into the details. So before talking about the AC analysis, obviously we need to recall one thing. And so in terms of the applications, the transistor can work as either a switch or amplifier, right? So working as a switch is just having two different states, on or off, right? And working as amplifier is actually can amplify the input. But be careful, the amplifier or say amplification of application is referred to AC and AC input only, okay? The DC supplies are not considered or not even called as input. Okay? This is a very important concept in your head. Okay? We won't call the DC as input. DC as what? DC supply, DC biasing. Okay, and a lot of text book call it biasing. Okay? Biasing means nothing but DC supply. Okay? DC supply is biasing the operation Q point to somewhere you want. So we won't call the DC as input. Even if you call it as input, okay, you still need to be very clear that it's not the input to be amplified. Right? AC small signal input is the signal to be amplified. Therefore, it should be called input of the circuit. And here we can also recall quickly the previous lecture. Remember here, when we identify the common circuit, we need to identify who is input, who is output. And when we identify who is the input, we are referring to what? VI, right? V sub I, which is what? AC input, AC signal input. Okay, so when you call an input to a circuit to amplifier, it means the AC. It is not meaning the DC. DC just the top here, bottom here to provide external power. Call it power supply or say biasing. Okay, continue here. If this is clear, then we can go ahead to talk about the amplifier. To work as a linear amplifier, the Mosfet needs to be biased or say DC biased into saturation region. Right? And this is very important. We have three regions in the IV curve. The saturation is the region to make the amplification happen. You make sure your DC somehow is locating your Q point or say that the operation point into the saturation region. If so, then MOSFET works as linear amplifier, which means your output voltage here is equals to a constant gain times the input. Once again, both output and the input here are referred to AC. We're not talking about DC. The MOSFET, the transistor won't amplify DC. It won't do that. It won't only amplify the input AC. However, you need to also be very careful. There's another concept very easy to feel confused, which is the output signal. Your output signal V0, say, once again, use the example from last lecture. Your output is this V0 right here. This V0 might contain DC. Don't be confused. This output might contain DC. Well, of course, not to this particular one because you have output coupling. However, to this one, it might including DC here. Why is that? Because you have both DC supply and AC input. And then you try to find any particular signal, voltage or current anywhere in the circuit. They're always the results of the superposition. Superposition, obviously, you have DC result plus the AC result. So your output, of course, is absolutely possibly having a DC and AC. Just that, remember, the gain we are looking for, or say the amplification we are looking for is referred to the AC part and AC only. Does it make sense? These are very important concepts. Okay, these are very, very important concepts. And operation is described by load line, and IV curve. This is a little bit hard to understand, actually. This is imagine if your gate is the AC input, okay, your drain is the AC output. The common terminal is obviously the source, right? So your input VGS is AC, like this, like AC input. Your output is VDS. So how to understand this amplification then? The first is determined by this Q point, which is biased by DC analysis. Okay, so around this Q point, your input signal is actually swinging between among different VGS value, because it makes sense that VGS, as we said, is AC input. AC signal is time varying. Of course, the input voltage is swinging among different values, VGS value. Therefore, your operation point is gonna swing accordingly as well. Remember, the VGS determining which IV curve we are talking about. So if your VGS is swinging to different values, of course, your IV curve is gonna swing too. However, it's gonna swinging along the load line, which is from the DC analysis. So this operation point is gonna swinging back and forth, is actually projecting onto the VDS, which is the output, is sinusoidal as well. Yeah, this is how the amplification is happening, actually, explained based on the given IV curve. If this is a little bit too abstract, you can review the recorded lecture later to catch up. So after explaining how the AC amplification, the concepts about it and how it works, let's get into the AC analysis a little bit, okay? So first thing is so-called small signal model. Small signal model is meaning the small signal model of the transistor, Mosfet itself. Okay. And resulted further AC small signal circuit is the circuit not only containing the small signal model of the transistor, but also the rest of the resistors and AC source. And obviously no more DC source because they're talking about AC. Okay. The DC source is going to be eliminated. For example here. The given circuit is here is we are seeing a N-channel MOSFET. And we're seeing RD. They're seeing AC input VI. They're seeing DC supply VDD and another DC VGS, which is quite abnormal. This VGS here, VDS, generally speaking, we won't have it. If we do have it, we're gonna add a input capacitor to couple it off. Anyways, assuming we have these DC, AC, and the resistors, and the corresponding AC circuit is what? AC circuit is, obviously, we get rid of the DC source, right? We get rid of the, we short this DC, we short this DC too. So look at the gate. Gate connect to the positive polarity of the AC input. Here we go. It is right. Negative polarity of the AC input is what? Shorted to the ground. And it is, no problem. Also, the drain of the MOSFET is connected to one terminal of whom? RD, right? The drain here connect to one terminal of the RD, no problem. The other terminal of the RD is up here, is where? Shorted to the ground. And it is here. You see the equivalence? And meantime, who is the output? Output is out of, from the given circuit. Output is out of where? The drain, right? And it is. All right, everything is checked. So these two circuits are equivalent. Just that the right-hand side is the AC equivalent circuit. AC circuit. Okay. We're getting rid of all of the DC source. And if any capacitor, what do we do? Anyone knows? If any capacitors in the given circuit, what do we do about them?
You short them.
Assure them. Very good. Assure them. So we're gonna end up with the AC equivalent circuit. Okay. This part is not something new. This part is not something new. The new things is the following. Okay. The new things is the following. So first of all, be careful. This circuit here is so-called AC equivalent circuit, but in our mind, we should understand it as this is not a small signal circuit yet. It's not a circuit we're really looking for yet. Until it is not. Until what? This transistor is replaced by so-called small signal model. Until then, it is not what we're really looking for yet. And before presenting the small signal model for the Mosfet, and there's some equations, some formula we need to be aware. We don't need to memorize, however, we need to be aware of the existence of them, right? But first of all, the drain current and the VGS here, there's a relationship like this, where the GM is a new constant called transconductance, new constant parameter, and it is calculated in terms of Kn and IDQ. So here, be very careful. First of all, look at the letters, okay? It's case sensitive. In other words, this ID here, up here, is AC ID. This VGS is AC VGS. Listen very carefully. This guy is not the DC result ID. Okay. This guy is not the DC result VGS either. Be very careful. Such mistakes happen a lot, and introducing a lot, a very significant point loss in exam. Okay, remember this. If you are using the DC results into this AC small signal model, that is absolutely conceptual mistake. You're going to lose a lot of points for it. Did I make myself clear?
Yep.
All right, thank you. Okay. Remember, absolutely remember, no matter what, you don't make such mistake. They are case sensitive, indicating DC and AC. And imagining the superposition result, you can't mix up the results to each other. Okay. So DC analysis result can be used, however, not here. Where's the DC result you need for AC? Here, you see, once again, case sensitive. Does it make sense? It's a capital I. The DC result, this is the ID. This is the DC result. Okay. This guy is the DC result. You probably want to take some notes on this page 5. Saying on page 5, you need to be careful on these things. I know my writing here is terrible, but that's the best I can do. Okay. So IDQ here is the DC analysis result. Okay, this is the ID. This is a real ID. The Kn is whom? Anyone remember? Kn
that was a parameter that's usually given.
That's right. And for DC analysis as well. Remember? Okay, so this Kn is also a parameter given for DC analysis. Okay. So this is find the AC small signal parameters GM, transconductance. Okay, you're applying DC results. And we also have a resistance here, output resistance or not. This is something new as well. Okay. Output resistance of the Mosfet. It equals to VA divided by IDQ. Once again, this IDQ is the DC analysis result. Okay. And VA is something given, is the early voltage. We learned the early voltage previously already. So VA is something given, early voltage. And also be very careful. This is another thing very easy to make mistake. Output resistance is and always is between drain and the source. Do not think of ground. Maybe source is ground, maybe drain is ground, maybe none of them is ground. It has nothing to do with the ground. You just make sure or not it's between drain and the source. And this is another very easy to make mistake. It happened too often in the past. It's always between the drain and the source. Okay. Rather than anything to do with the ground. Right, these are some formulas we definitely need. And furthermore, this is the page. What do you want? You want to print it out as one of your handouts. Use this guy in the exam. Okay, you definitely need it. You definitely gonna need it. And most important page for today's lecture. Okay? No matter how many slides I'm gonna teach today, page 6 is the most important. Okay, you want to print this page out as one of your handouts, part of your cheat sheet, or say. Okay. First, it is repeating the calculation of two parameters. One is transconductance, the other is the output resistance. Okay. We definitely need both. We definitely need both for the small signal model for the transistor. And then let's take a look at the this model. Remember, this model is for the transistor and the transistor itself only, okay, without involving any other resistors, capacitors, or input source. Okay, this model is for the transistor itself only, nothing else. Right? And the model is what? Gate is here, source is here, drain is here, and between the drain and source, what do you have? What this guy is? What is it? Anyone knows what this guy is?
Is it a dependent current source?
Depending current source. And what dependent current source? We have up to 4 types of dependent source, right? Remember? This is what? Because dependent current source is just half of the name. Does that make sense?
Voltage dependent current source?
Very good. It's voltage dependent current source. Very good. Now, first of all, why is the current source? Because of the symbol. Second, why is voltage dependent? Because your value, the current value, is depending on the voltage rather than current, VGS. Does that make sense? So this is a voltage dependent current source. And the VGS is where? VGS is very meaningful. Okay, the subscript is telling you is the voltage across gate and source, and also the gate must be the positive polarity. Source is the negative. Okay, they're following the order of the subscript. Every single detail has a reason behind it. The voltage between the gate and source is the dependent voltage here. Okay? this is telling you the current here, flow through. This is because this is the current source. Okay, and R naught, as I emphasized, is always between the drain and the source, regardless ground. This is the model for N-channel MOSFET. Okay, once again, this is for N-channel MOSFET. Okay. How to have the P-channel MOSFET is the key for today as well. Let me present the P-channel. Under the dot camera. And the way I'm gonna present it is like this. Okay. So first of all, N channel. And then I'm using the red to represent the P channel. Okay. Of course, small signal model. Small signal model. N channel, I'm just a copy and paste here. N channel, just dependent source. Right. To easier differentiate N channel from the P channel, I'm repeating the most of the circuit while keeping the difference in red color. Okay. Oh, of course, here this is a VGS. So in red, once again, representing the P channel. What's the difference? Terminal remains. Okay, terminal location remains GSD. However, the difference is we're not naming the voltage between gate and the source as VGS, not anymore. We are naming it as VSG. And flipped polarity, once again, is follow the order of the subscript, VSG. Remember in the DC analysis, they're using VSD, VSG, right? Rather than VDS, VGS, right? Here is similar. Here is similar. What else different? Remember in DC, we know the current flow direction is opposite between two types, right? So is here. Okay, so is here. So current dependent source remains this location. However, the current direction is flipped. It's not from drain towards source, but the other way around. And the current value is equals to GM times VSG, obviously. So once again, the red color is indicating the difference from N. Difference from N. The rest of the thing was same, exactly same. Okay. So P-channel MOSFET is using the red here. Any questions? This is the most important thing for today's lecture. Okay, and once again, you don't want to miss any detail.
So does the ID flip direction as well since the current source is flipped?
Correct. 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 Any other questions? So once again, you want to print out this page 6 as your handout by side all the time. Because even before the exam in the regular lecture, guess what? We're going to do some in-class exercise, right? You need these formula. You need this formula. You need this model too. Does it make sense? If you don't have them by side, then in the lecture exercise, what are you going to do? Stand by? No, that's the last thing you want to do, okay, during the lecture. You must engage. Standing by is the last thing you want to do. This is the small signal model for the transistor itself. Okay, once again, it's for transistor itself. And further, we obviously need to extending the circuit, right? Extending the transistor to the entire circuit. How are we going to do this? How are we going to do this? You need to follow certain order. So first, this is repeating the small signal model. Here. This small signal model here. Transistor itself, just the equivalent to this small signal model. Now let's assume we have a transistor circuit, which not only include the transistor, but also the rest of the DC supply, AC input, and the resistor, right? How we find out the ultimate so-called small signal circuit. That's the circuit we're really looking for. How we find it. Here, I'm showing you the result. And listen carefully how we get here. The point is obviously how we get here. That's what we gonna be assessed. First thing you need to do is place the small signal model, which is contained in red box here, right in the middle of your paper. This is just a copy and paste. Very easy first step. Of course, before doing this, you need to identify what? N channel or P channel, right? Because we have two different small signal model. Okay? Place this model right in the middle. And then extending the circuit terminal by terminal. What does it mean by terminal by terminal? We have only 3 terminals, okay? G, S, D. Only 3 terminals. Okay, so it's not any random number. You have and only have 3 terminals. So you are extending your circuit terminal by terminal. First of all, let's begin with the gate. Going back to the original given circuit, the gate connect to where? Positive polarity of the VI, right? Okay, the gate connect to positive polarity of the VI. The negative polarity of the VI is shorted to ground, right? Because once again, this is the AC circuit. So negative terminal of the VI go to the ground. We're done with gate. Next, the source down here. First, going back to the original given circuit, of course. The source is here. It's nothing but the ground. Very easy. Okay, short your source to the ground. That's it. Last, the drain. Right, you're trying to extend the drain. Okay, going back to the original given circuit, the drain is here. The drain, first of all, is what? The drain is the output. So don't forget the drain is output. Here we go. Second, the drain is also connecting to RD. Okay, the drain connecting to RD. The other terminal of RD is shorted to the ground. Okay. We're doing so as well. The other terminal of RD is here, shorted to the ground. Done. Is this procedure clear? Any questions? All right, if this is not too bad, we can go ahead to try more, and we can go ahead to try more. So to this circuit, this is repeating the obtained a small signal circuit. Okay, this is repeating previous page. What matter is, what is the voltage gain? Okay. This is something you want to take a note. When we conducted AC small signal analysis, we are looking for the voltage gain, AC voltage gain. We are not looking for the output. And remember this, we are not looking for the output. Okay, because the input won't be specified. Won't be, will not be specified. So there's no way for you to be able to find the output signal. Okay, so both input and output, in other words, are unknown. Therefore, the only thing you're able to find is the gain. Okay, remember this tip, because it happened too often in the past. Students trying to find the output signal. However, they can never do that. Okay, they can never find the output signal because the input signal is not given. Both input and output are unknown. You can only find the gain between. Only find the gain between. So don't consider VI as something given, because it is not. It's unknown. So is V naught. Then how to conduct the circuit analysis? Then it's nothing but the once again 235 knowledge. 235 knowledge. I'm presenting the solution here, and we try to take a look to see some sense here. So first of all, we have a so-called output equation. Output voltage here is equals to what? It's an open circuit. It's it as an open circuit. Okay, don't worry about it. Output voltage therefore is depending on what? How about the current here times parallel between these two resistors equals to the voltage across these two resistors, which is nothing but our V naught. Does this make sense? And what is the current here? Telling you GM times VGS. This is the value of the current. However, you need to be very careful. Why we have this negative sign here? Why? Anyone knows why we have negative sign here in the equation? Any reason for this negative sign? No one knows? Well, the current here is here, right? This, in other words, this current is GM VGS. Now, how about the current flows through the R0 and RD? They're all upward, right? Because of the KCL at this node.
So the current would be flowing the other way in the equivalent circuit. Is that why it's negative?
What do you mean by the other way?
I guess I shouldn't say the other way. I'm just trying to think about it.
Well, the current is, you can tell, is upward. Right? You have a current upward through a resistor. What is the result of the voltage across that? Positive here, negative here. Does it make sense?
Yep.
So this sign is polarity is opposite to the VDS, or say the V naught polarity. Exactly opposite. That's why you have a negative here. So you have a resistor here. If you have a current from top to bottom, it's I. It's very easy. The V across this resistor, V, is just equals to I times R. with positive polarity on top, negative polarity on the bottom. Right now, the current is flowing the other way around, and the introduced voltage polarity is flipped as well. It must be. It must be.
Yep, it makes sense.
Yeah.
I was making my mistake from last time, and I was looking at the arrow again, and I got mixed up.
All right. All right. Yep. This current direction is very meaningful. Okay, it's like going this way, and the current going towards left, and then therefore the current through the resistors are upward. Everything is following the given. Okay, following the given. It's not random. It's not random. Okay, this is the output Ohm's law, right? It's nothing but output Ohm's law. This equation, nothing more than Ohm's law. And then inside this equation, you can also see a VGS is what? VGS is something we don't need because we need the gain. The gain is in terms of VI and V naught. So we don't need VGS. And also VGS is equals what? VGS, how about, is exactly VI, because these two voltage are parallel. So substitute VGS by VI. You end up with this equation here. And inside of this equation, you have two unknowns, V naught and VI, right? V naught and VI. Divide by VI on both sides, you receive V naught over VI equals to negative GM times parallel between R naught and RD. Does it make sense, this procedure? This is the easiest case in the sense that you only have one resistor RD here. You don't have any other biasing resistor, not yet. But this just give you a rough idea. And once again, and at the end, what you're seeing is if you count VGS as the third unknown, okay, V naught, VI, there are first two. VGS as the third unknown. How many equations you have? Anyone can count? How many? I mean, can you see how many equations we have? Actually,
That's just two equations, right?
exactly right. Okay, exactly right. Two equals, of course. So two equations, three unknowns. The number of equations is one less than that of the unknowns. This is once again verify what I just said earlier, that we are not able to find a V naught, we are not able to find a VI either. We are not able to find a VGS. We can't find anything individually. And the only thing you can find is the ratio between any two of them. Okay, this should be the case in your problem solving as well. If you're seeing you somehow receive the V naught signal value, I'm sorry, you're 100% wrong. Okay? You're 100% wrong. Somewhere definitely wrong. Did I make myself clear?
Yep, think so.
Good, good. Okay, remember, this is one of the tips. Just like back in the DC analysis, what you should have. Same number of unknowns and same and the number of the equations, right? Must be same because we are looking for individual unknown. ID, VGS, VDS, right? But here in AC small signal analysis is not the case. We can only find a gain, which is a ratio between two unknowns. We can't find V naught. VI is not given either. Okay, so forget about those. You need to somehow eliminate the VGS so that you only have V naught and VI left. So I'm seeing here is a Q&A happening. Very good between Daniel and Kevin. I like that. Well, this is one of the drawback of the online teaching and learning, because in the regular in-person class, you guys can talk to each other during the lecture. I won't mind that, actually. It's very helpful too, but this is obviously not quite possible, except you're violating the rule, okay, social distance the rule. All right, any questions before we move on? All right, we can move on to here. Give you guys a little bit time to obtain the AC small signal circuit for this one. In the meantime, I'm giving you this guy here as a handout to help you. All right, how about that? We'll try this circuit to find the small signal circuit, including the transistor model, including the rest of the circuit element. So go ahead, give you guys 2 minutes. Do it. Extremely important in-class exercise. Can you guys see everything clear enough by this dimension? I mean, this size of display? I never asked this before, but any trouble of seeing things clear?
If I maximize the screen, I can see it well enough.
Yeah, without doing that, I probably a little bit hard. How about others? No trouble?
Big enough on my laptop.
What was that?
It's big enough on my laptop.
Okay, good. I see. All right. Thank you, too. And 2 doesn't have any trouble either. Good. All right, go ahead. Do this. All right, we can see how we end up with a circuit from the scratch. First step, as I ever said, place the correct small signal model of the transistor right in the middle of the paper, right? So which one we should place? We need to, first of all, identify this is the P channel, right? This is the P channel. This is not N channel. So P channel small signal model is like this. Right? right? This is a transistor, and transistor itself. Once again, P channel. Okay, you can't use the N channel, then they're completely wrong. Followed by extending the circuit by terminal, right? So which terminal is the easiest one in the circuit? Which terminal is the easiest one?
I'd say S.
Yep. And it is what? Ground. Right?
Yep.
The source is nothing but ground. And next, we can extending the gate. So gates, according to the given circuit here, is connect to the input AC. Okay, input AC, VI, positive terminal, of course. Negative terminal of the VI is nothing but the ground as well. So short here then. Right. Then we are done with source and gate now. Okay, the only terminal left is the drain here. So the drain, first of all, is the output. Okay, never forget this is the output. You need to label it as this. You know where is the output. Second, the drain is also connecting to the RD. The other terminal of RD is the ground. Drain connect to the RD. The other terminal of RD is the ground as well. Does everything make sense? And here is the solution. All right. And also following the same idea for solving the circuit, we end up with these equations. Pretty much here is very easy. So once again, the VSG is equals to what? VSG equals to negative VI. Okay, does it make sense? From here, VSG equals negative VI, and V naught this time is equals what? Positive GM VSG times the parallel between R naught and RD. So here is positive, and here is negative. Take a look to see if it makes sense, especially these two signs. Okay. Once again, this positive is due to the downward current flows through R naught and RD. And this negative sign is due to an opposite polarity between VSG and VI. Does it make sense? Any questions?
I have a question.
Yeah, go ahead.
Can R naught and RD be in series?
Say that again?
Can R naught and RD be in series?
Are V naught and RD?
Yeah.
V naught and RD are parallel. And also RD is a component with two terminals. V naught is a signal. So basically V naught is from here, positive here, to negative here, right? So pretty much this, sorry. So this is V naught, right? RD is here, exactly parallel. Of course, we never say one voltage is parallel with one resistor. That sounds weird, but actually they're parallel. Okay. Or say the V naught is the voltage exactly across the RD. That is a much better description. Does it make sense?
Yeah.
Are you talking about R naught and RD?
Yeah, I'm talking about Kevin. Yeah.
R naught is between the drain here and the source here. That's why it is always here. RD is between the drain here and the ground. And the ground is nothing but the source in this particular circuit. That's why R naught is parallel with RD. My point is, you can't try to remember like R naught is parallel with RD all the time. No, absolutely not. If you try to memorize in that way, no, it's going to be wrong. Okay. All right, any other questions here?
So that last equation there, it means AV is roughly equal to, and then that if RD is like way smaller than RO.
Yes, this is actually a little math. First of all, R naught output resistance, generally speaking, is very big. It's tens of kilo ohm. So if your RD is not very big, and then the parallel in between is what? A little bit lower than the lower one between two parallel. Understand what I'm talking about here? What I'm saying is this. You have resistor 1 and resistor 2 parallel. It equals to what? I know the formula, however, without using the formula, there's a tip here. So assuming one is less than the other, the parallel is approximately equals what? Or say the parallel between two is less than the smaller one between two parallel. That's why you're going back to here. So R naught parallel is RD. If the RD is smaller one, then the parallel between two is smaller than RD. Actually, a little bit smaller than RD because its R naught is way bigger. That's why parallel between these two is approximately equal to RD itself. R naught is too big to affect the parallel resistance. It also makes sense, right? If R naught is very big, that means what? They're in parallel, then the total current will barely go through this R naught, right? Because it's too big resistance. The majority of the current, or say almost all of the total current, going to flow through RD. So only RD is significant. R naught is not. Right? Does it make sense in this way too?
Yep, makes sense.
All right, thanks. Any other questions or concerns?